Okay, so here's a second example of using Hess's law to calculate the enthalpy change of a process by breaking it down into component reactions or different chemical processes or physical processes. So for example, if we would like to know the enthalpy change for converting 55 grams of liquid water initially at 20 degrees Celsius to steam at 250 degrees Celsius, there's really no straightforward way to go directly from an amount of liquid water at its one temperature to an amount of steam at a second temperature, because in addition to taking energy to heat up the water and heat up the steam, there is also the energy required for the conversion of liquid water to steam, that is the boiling or the vaporization. So for example, if we look at this, what is called a heating curve here, we can see that if we start out with liquid water, we can calculate, as we've done in the past, how much energy it takes to heat up water, right? And this is basically our heat equation. Q is equal to Sm delta T. We'll see this again in just a moment, right? So it takes, if we're giving a sample of water a constant amount of energy, initially that liquid water will heat up until it reaches the boiling point of water. At that point, all additional energy will be used to vaporize that water, and the temperature of the water will be held constant at that 100 degrees Celsius until we've reached the point that we've boiled away all of our liquid water and has become a gas, and now that steam can be heated. Okay, and so what we're going to do in addressing a question like this is to break down our process into a number of different steps. Okay, now we've talked about how to calculate heat energy for heating, that is for that we've talked about specific heat capacity and how to calculate the magnitude of energy to undergo a given temperature change for something like water with a known specific heat capacity. We have not talked too much about the energy requirements for these changes of state, that is for things like boiling water or vaporizing water from liquid to steam, or converting ice into liquid water, what we call the heat of fusion. So in both of these phase transitions, going from a solid to a liquid, or for a liquid going to a gas, these are endothermic processes, that is, that requires energy to go from a liquid to a gas, because we need to break the intermolecular attractive forces that are holding, in this case, the water molecules together as a liquid. And now when we vaporize them to a gas, we've broken these intermolecular attractive forces, and the gas molecules are now moving around quite freely from one another. Okay. Now the energy requirement for this conversion, we call this conversion the heat of vaporization, or the enthalpy of vaporization, delta H vaporization, and this is a constant for a particular substance. So in the case of water, it takes 40.6 kilojoules to vaporize 1 mole of water. So delta H of vaporization is equal to 40.6 kilojoules per mole. Similarly, going from a solid ice to liquid water, we have what is called the heat of fusion, and this delta H, we also need to break some of the intermolecular forces that are holding the molecules of water together as ice to form liquid water, and this only takes 6 kilojoules per mole. But let's focus on the heat of vaporization. So it takes 40.6 kilojoules to vaporize 1 mole of water. So now when we come back to think about this problem, the enthalpy change for converting 55 grams of liquid water at 20 degrees Celsius, how much energy does it change to convert that to steam at 250 degrees Celsius? So in this process, we don't really have a simple way to go directly from the liquid to the steam at a different temperature. But what we know is that we can break this down into different components, and Hess's law will tell us that we can simply add up the enthalpy changes of each of those components. So we know how to calculate going from liquid water at 20 degrees C to 100 degrees C, its boiling point, and we are simply going to say that Q is this delta H is the same as Q, our heat, is equal to SM delta T, or S is our specific heat capacity of liquid water, 4.184 joules per gram degree C. Our mass here is 55 grams, and our temperature change, T final minus T initial, is 80 degrees. So when we plug these into our equation, we see that delta H1 here is equal to 18.4 kilojoules for that 55 grams, okay, or 18,400 joules, and we're going to leave it in kilojoules here. Now we're going to take this 55 grams of water at 100 degrees C and we're going to vaporize it. And our heat of vaporization tells us that for 1 mole it takes 40.6 kilojoules. So for 55 grams, we're going to convert that to moles using our molar mass. So 55 divided by 18.02 grams per mole and multiply that by our heat of vaporization, telling us that this delta H2 is equal to 123.9 kilojoules. So it takes 18 kilojoules to heat our water to the boiling point, then another 124 kilojoules to vaporize all of that water, and now we have 55 grams of steam at 100 degrees C. We simply need to heat that up to our final temperature of 250. Again, this is just a heating event, so we're going to use Q equals SM delta T, which is equal to delta H3, but now our specific heat capacity, this is no longer liquid water, but it's steam. The specific heat capacity of steam is 2 joules per gram degree C. The mass is still 55. Our temperature change is 150, so our net delta H3 will come out to 16.5 kilojoules. Okay, so now we have all three of our components. We've heated our water to the boiling point, we've vaporized our water, and now we've heated our steam to our final temperature. And now to get the net enthalpy change for the whole process, we simply add these three components, delta H1 plus delta H2 plus delta H3. And we see that the net enthalpy change, delta H3, is equal to 18.4 kilojoules plus 123.9 kilojoules plus 16.5 kilojoules, or for a total of 158.8 kilojoules to heat that 55 grams of water at 20 degrees C up to steam at 250 degrees Celsius.